So we're back. I thought what I would do is try and fix my computer, but I found it was not fixable, oddly enough. This is going to bug me for quite some time, I think. Seriously, nobody knows how to do this? I thought you guys were Windows people. Maybe I should switch to a Mac. I never have this problem.
Did they replace the projector so
No. No. Nobody's replaced the projector. So what I wanted to do was I wanted to describe more of the details of how to do remote method invocation so that you all would be able to do this on your own. And I can kind of tell you a little bit about it. What you want to do is you want to create an interface that's held in common by both the remote object and the client object. And this interface is something that you would expect your server to implement. When it implements the interface, it would expect it to implement not just the interface, but to implement a throwing of the remote exception at runtime. So what can happen when you have a remote object is you can have improper communications, you can have a timeout, you can have mechanisms that prevent you from ever returning. You could have your server crash, for example, and when those things happen, you'll never get a call back. So the question of how you handle unreliable communication in RMI is one of those things that kind of remains open. What happens if I said A equals F of B and F never returns? How do I handle that problem? What do I do about it? You could time out, but then you'd have to have some idea as to how long it takes to do the computation. If the computation takes an hour, would it be okay to time out after an hour and 10 minutes? What if it just happens that you timed out a little too soon and you just needed to be a little bit more patient? So this is one of those things where you really need to know the implementation and its execution time in advance. What I like to think about when I think about RMI is I like to think about the harder problem, which is how do I segment a normally sequential operation into one that is parallelizable. And I think that in and of itself is the most difficult of problems. Parallelizing a sequential algorithm is never easy, and the automation of the parallelization of sequential algorithms is the holy grail in computer science. Everybody is trying to solve this really important problem, and nobody has a good solution. That is to say, humans are needed to think about problems deeply in order to be able to divide them up efficiently across multiple machines. At least that's the current state of the art. I myself have tried on several occasions to automate the network of workstation problem, which is to try and get a network of workstations to work as a single computer. There are a few different ways available to us in order to be able to exploit multiple machines. You probably are familiar with some of them. Have you ever heard of the SETI project? Does anybody know what SETI stands for? The search for extraterrestrials. People use SETI screensavers in order to facilitate that search. It's a signal processing problem that's eminently parallelizable. And what they do is they volunteer their CPUs by running the SETI screensaver. They have these screensavers available for what they call the Berkeley BOINC project. And with the BOINC code, you can volunteer your CPU when it's idle for a whole bunch of different other projects as well, including genome search projects. and cryptography projects. So in effect, what we did as a team here at Fairfield University is we created our own screensavers. And they were meant for Java RMI. And so with the screensavers that you launch locally on, let's say, all the machines here in this room, you get to volunteer the computers into a lookup server so that the lookup server can then find CPUs that are idle and then use those for delegating tasks. So if you think about it, a computer spends most of its time idle in this campus, right? All summer long, all night long, most of the day. And during that time, it's throwing off heat, it's sucking down power, and it's quietly depreciating. In fact, rapidly depreciating, because last year's computers are worth less than half of this year's computers. So what we can say is that in a couple or 3 years, the computers are on a replacement cycle. And this means that they move down the food chain to other systems. And you see this all the time. You go into the machine shop, and what do you see? Computers from 5 and 6 years ago dedicated to things like numerically controlled milling machines. So as it happens, these are classroom computers that have been retasked for specific applications. Generally, they're kept off the network because they can't even be patched to a modern version of an operating system. But we don't care as long as they can be used for our machines. So it makes sense, right? It's green. Everybody should be able to volunteer their computers into the giant parallel virtual machine that is the network of workstations running some screensaver. After all, we get our computer back as soon as somebody wakes it up. So when we do an invocation and we marshal our parameters across the network, we're really marshaling what looked like a reference, but which ends up being an actual value pushed across the network. So when we have these remote objects, we can have, I could call it, references that we can invoke. But in effect, when we invoke these references, what we're really doing is we're taking an address that's local to our machine, going to the instance, serializing it, then marshaling it as a parameter across the network, essentially turning it into a value, and then having it, I'll say, remotely reconstituted into a reference at the server. And so what that means to me is that all reference data types must implement serializable, and even though we can't implement serializable in primitive data types, we know that all primitive data types can be serialized. Even arrays of primitive data types can be serialized. So if I have an array of int or an array of char, it can all be serialized. Strings are already serializable. And of course, anything that you want to pass to the remote object, including, let's say, payroll, would have to be serializable. And the other thing that's interesting and unique about RMI is anything you do as an invocation must throw a remote exception. And so that remote exception is in there because we know that communication is typically held as unreliable. Let's go back to the code. I like to do a little PowerPoint and a little code example every now and then, because otherwise it gets too boring. So let's think about inheritance. Right? When you think about inheritance, you get your method implementations either from the method body in your subclass, or you get it from the method in your superclass. But inheritance in a single inheritance language, like Java, says that you cannot have two superclasses and inherit methods from both. So what does that mean in terms of getting code from other instances? How would you get that code from other instances if you can't inherit from it? Interfaces will give you multiple inheritance of specification but not implementation. Interfaces will give you multiple inheritance of constants, but if two constants have the same name, it becomes a compilation error. Multiple inheritance for specification is okay, right? Because if you have multiple inheritance of specification, what that means is if you have two methods with identical signatures, it doesn't matter which method overrides the other. But if you have multiple inheritance of implementation, not specification, but implementation, then if I make an invocation, how will I know which method gets invoked? Let's assume that I have two classes. One is called the date class, and the other is called the customer class. When I convert the customer class into a string by invoking the toString method, it says Joe Schmo. When I invoke the date turn it into a string, it prints out the date. That's fair. Now let's assume I have multiple inheritance, and I subclass the date customer, and I convert the date customer into a string. What does it print? Does it print the date, or does it print Joe Schmo? In a multiple inheritance type language like C++, the way that is decided is by virtue of which class comes first. So if it's a date customer and it says I inherit from date and then from customer, the date's toString invocation overrides or shadows the customer toString invocation, and therefore it prints the date. But if you change the order and put the customer first, it prints out the customer and it prints out Joe Schmo. In the parlance of the professional, this is known as topological sorting. In topological sorting, what we do is we inherit depending upon which class comes first. That's the typical rule. People found this to be a fruitful source of bugs. As a result, they made a decision. The designers or progenitors of Java decided to leave off multiple inheritance. And so what that means, that is multiple inheritance of implementation, but not multiple inheritance of specification. So in this way, when two methods are shadowed against one another, there doesn't have to be any mechanism for disambiguation, such as topological sorting, in order to decide which method gets overridden by the other. So when we're dealing with a mechanism for reusing code and we're denied access to the language feature of multiple inheritance, what do? We can't reuse code by subclassing, right? Because if we do, we can only subclass one class, and then we're done. What about the other classes? Do we push them up the subclass chain? Certainly not, right? Because then it would be just giant chains of subclasses. And we'd have fragile base classes, which would lead to a constant recompilation problem. That is, a small change in one class that's a base class would cause us to have to recompile all the subclasses. And that would happen all the time for every small change. So what do we do? How do we reuse the code? Huh? Well, abstract classes can have code in them, but we would still have to subclass them in order to inherit that code. Well, if I have an instance of an object that knows how to do something, I can just invoke that method on that object. And we call that composition instead of inheritance. And so in a single inheritance language, we favor composition over inheritance for code reuse. Some people call that method forwarding. Other people would call that delegation. That is to say, we delegate the implementation of the code to some other class, some other instance, and then we proceed to invoke that method on that instance. That's delegation. So in effect, what happens here is in RMI is the same sort of thing. We're doing a kind of delegation. We go through a proxy to the remote server, and then we proceed to delegate the implementation onto the remote server. So in this case, it's a matter of having composition only with the thing that you're compositing residing in a remote place, on a remote virtual machine. So now let's have a looky-loo and see what we can find. Here is an object which is said to be computable. So the computable interface, let's have a look at this since I can't see my screen. The computable interface sounds like a relatively simple thing. It extends remote, so it can be a remote object. It has a method in it which returns an answer which is said to be serializable. It throws a remote exception in case things go wrong. It can remotely print onto the console an arbitrary argument. However it does that, I don't know, because I have no implementation for the print line here. And the print line can also throw a remote exception. What are the limits to this computable interface in terms of things that it can compute? What's it got to have? An answer that's serializable, right? Got to. But that's not too bad. That's not a big constraint. What about the constructor? Is there any limit to what the constructor is? And a lot of times computations take arguments. So if you want to, you can implement this computable item with an arbitrary constructor. But that constructor invocation, well, that better be past a whole series of, I'll call it marshallable parameters, serializable parameters, parameters that can pass across the NAT. Moreover, if you put a constructor in, I guess it better throw a remote exception if you're going to construct remotely. What if you construct the computable element with a setter? You could set those things up remotely, that's for sure. So you could put in an arbitrary setter. So the computable element could in effect take arbitrary setters, it could have constructors, it could have a whole bunch of things that it needs to compute. We don't know how long they take. Presumably it needs to be CPU bound. It must return a serializable instance. Could be an image. It's not too bad as a constraint. It's sort of a general purpose thing. It's a little bit simple, but I like simple. I think simple is a feature. So here's my computable server. All right? He implements computable, so that means he has to have the ability to compute something. And what does he compute? Well, not much, really. On a variant of the Hello World he says, goodbye world. And he returns that string as a serializable instance to the invoker. That's fair. The constructor throws a remote exception. Doesn't seem to take any arguments, but that's okay. Doesn't have to. The print line, that can also be invoked remotely. And when we call print line, serializable instances must be passed. Strings, for example, that's legit. And then somewhere on the remote console, there'll be a print statement invoked, and stuff will come out, and we'll see it. So I can go from my computer to some remote computer called print line, and the stuff comes out on the console. What do you think of that? Good, right? Could I test this locally with a main method? Sure. Why not? But first, I'd like to try and see what the server looks like. So let's see if there's anything else in here that we'd like to look at. And I think this is interesting. We have talked a little bit about sockets. And when we use sockets, what we did was we had a TCP/IP address, and then we had a port. And we made a connection to another machine at a specific IP address with an application listening to that port, accepting a connection. That's called unicast TCP/IP protocol. Unicast means one-to-one. So you're trying to reach out to a single machine. But if I want to take video or audio or any kind of multimedia and broadcast it to all these machines, I don't want to create an individual socket to each machine. What I want to do is I want to take UDP/IP datagrams, drop them on the network, and have all these machines receive them at the same time in a broadcast connectionless protocol. That's called multicast. So multicast is a substantially different and intrinsically more efficient way for one machine to communicate to many. Multicast enables me to flood the network with packets that get routed to all the machines. Well, if you could flood the network with packets, would you? Does it sound like a nice thing to do? Well, suppose I took a packet and I dropped it on the network, and it ran through the routers, and it ran through the firewalls, and it got on the internet. And then it spread all the way around the world.
Like a virus?
Like a virus. And then everybody else did the same thing. What would happen to the internet? It would come crashing down. Badly. And quickly. And that would be it. So there must be a reason why that doesn't happen. Because here in the new age of bad people and script kiddies, anybody who knew about that kind of a exploit would immediately exploit it and crash the network. So how would that stop? How could we stop that? Those multicast packets from running wild, bloodying the streets, killing passers-by and Googlers. How would we stop them? Those evil multicasters. Can't stop it. That's it. We're done. We're done for. Tell the world the internet is broken. That's it. We're finished. Well, the answer is every multicast packet has a time to live, TTL. And the time to live is determined by the number of hops that you allow a multicast packet to traverse before it is killed. And every time a router passes a multicast packet, it increments the time to live. And typical time to live is usually 3. So after 3 hops through a router, bang, they kill the multicast packets. The only time when that doesn't happen is when you configure the router specifically to pass the multicast packets, and then what you've done is you've created what's known as a multicast backbone, or the M bone. The multimedia multicast backbone enables broadcast through an entire infrastructure. But that's for individuals who are able to administer smart hubs. They're able to set up those hubs to pass the multicast packets across the network. So if I'm trying to broadcast this lecture into your, let's say, secure firewalled infrastructure, you can create what we call a reflector. I can use unicast IP to get into the reflector, and then the reflector can use multicast to rebroadcast to the local area network. And so I can tunnel through the firewall, get into the infrastructure, and then rebroadcast through multicast in an efficient way. Because the last thing I want to do is connect to individual machines, because if I had to do that, then I would need to duplicate the traffic. And if there were 10 machines with 10 video streams going to them, it would swamp your network. So in a sense, multicast is a great way in which to avoid all of that. So when you see a unicast remote object, what that says is it's listening to a specific port at a specific address, looking for a single point-to-point connection using a socket. And it gave me an opportunity to introduce the idea of multicast. Let's look at that client now. There we go. Why is it looking like this? Chip. Page down. Look up server and execute. That's what I wanted. So now I've got this idea that we've got an RMI registry that we want to be able to rendezvous with a specific service. In my case, the service is going to be running at an IP address, but this IP address could just as well be localhost. If you want to run a client to rendezvous with the local host using a protocol, that protocol should be RMI. So RMI protocol is running in a layer. So if you think about it, there's this, I don't know, we call it TCP IP layer. That's where the unformatted sequences of bytes or streams go. Then there's this other layer on top of it, I'll call it presentation layer, where these presentation protocols exist, and some of them are HTTP. Well, here's one called RMI. And what that's doing is it's passing instances that have been serialized across the network and doing invocations with them. Here comes the registry. I can put it up here on the local host. Then I can go to the registry and proceed to look up this URL on that registry, cast it to something that's computable, and then I should be able to go in and print remotely onto the server and write, hey, this is cool. Good. I don't know how to pronounce that. So, first thing I'd like to do is I'd like to find out if I can run my server. Now, does the server start a registry? Looks like he says get localhost, look up server and bind with registry. Localhost gets the localhost, look up server, bind with registry. Gesundheit. Server IP address. Get localhost, IP address, compute server, server started. Let's see if this works. Run. What could possibly go wrong? Oh, look, I've got an address. And the server is started. Now, I can either use the local host or I can copy and paste this address in. So let's go into the compute client. Let's throw in the local host. And not to put too fine a point on it, if you go CMD, you can say ping localhost, and it responds with a very cryptic looking response. So localhost apparently does resolve properly to an IP address. So now let's go into the compute client and see what happens if we run. And now we've got an interesting problem. Security manager's null, but we couldn't look up the server. So I wondered if the registry was running properly. Let's examine this. We got the registry, we got rebind. He says the server started. I wonder if I need an actual IP address here. I'll throw the IP address into the local host. I don't think that's going to make a difference, but I'll try it anyway, just for fun. Oh, it worked. Ha! How about that? So it says compute returns goodbye. Let's see what the compute server did. Oh, look. It printed stuff out. So it actually needed the IP address. Localhost was not good enough for it. It wanted a proper IP address. So you'd need to know the IP address of your registry if you were going to look up these. Your server is. What kind of computer is that? It's a Mac. Ew. It just says waiting. What did you do? You ran the compute server, and it just says waiting. What happens when you run the compute client? Probably doesn't like it, huh? You need an IP address. You should have one. Are you on the network?
No.
You're on the fax staff network. I don't know if I'm on the fax staff network. No, I'm on the guest network. Can people ping my machine from their machine? Can you ping this address? Are you guys on the guest network? What network are you? Student. Oh. I don't even know if I can get on that network. Yeah, I'm on the guest network, so you won't be able to ping me from the student network. I'm pretty sure. That's a non-routable IP address. Well, putting aside the hiccup that Kyle had, has anybody got a Windows computer that made this work? No, really? It's busted everywhere? Did anybody try this? What's that? Mac? Brian?
Yeah.
That's a Mac? Oh. Huh. Does everybody here have Macs except me? What kind of computer is that, Arodi? PC. Oh, okay. Does it work over there? Oh, well, if you haven't tried it, then I can't. Yeah, you got to try these things, for sure. How am I doing on time? Oh, good. So I've got this mechanism that doesn't work on Kyle's computer. I don't know why. Why would it say waiting? I shouldn't be debugging the Macs while we're while we're sitting here, but I just would like to know. So here's the server. Is there anything in this server that says waiting? Are you sure you're running the same thing?
What does compute server have to show on whatever I have?
Is it in the net.rmi package?
No.
Oh, it's in the net.compute package. You're running the other compute server. That's the problem right there. There's like an elementary compute server, and then there's sort of the classic sample that I'm running now. So if you want to run the compute server, if you want to run this compute server, you want to run the one that's in net.rmi. That's why it doesn't say waiting when I run it. Because it's kind of making an assumption that you're going to run it on the local host for the purpose of testing. Waiting is a legitimate answer for the compute server, for the lookup server, because that's meant to operate on multiple computers. This one is meant to operate on the local host.
Maybe not with the client.
But the server works. So did you get an IP address from the server? And did you paste that into the client? Okay, and what are you getting, an exception? No, I got null as well, I think. For some reason. But you should have a let's see, where is the computer? It worked? Okay. Problem solved. So I've got this idea now that there's a mechanism whereby I can do computations. I can distribute them across the computer. I've already suggested a couple of applications. One application ended up being kind of like a Disney application where we do animation across different machines, and we like the idea of doing animation because it's CPU bound. Right? Each frame could take many minutes. What else can we segment across the network? Doesn't have to be computation, right?
Actions?
Do what now?
Actions? Like comments?
Sure, comments. Yes, you can have communication. So if you've got communications across a network, you can do things like telephony, or you could broadcast radio, or you could broadcast multimedia, whatever that is. Images, I guess, and audio. Actually, you need both, right? You need at least two kinds of media in order to call it multimedia. I'm pretty sure. What else can we do? Here's one. The stock market client. That opens up a whole bunch of different kinds of things you can do. Because now that we think about it, there's this finance industry. And the finance industry can provide all kinds of interesting financial services. And now we have a mechanism whereby we can go out and get the financial services and then proceed to look up stuff like prices of stocks or maybe financial data other than the prices of stocks. Time and tick, for example. So here comes an interesting idea. We can create our own stock market price server. And in our stock market price server, we've got a little implementation. He's doing the same thing that we did before, subclassing the unicast remote object. He implements the so-called stock market interface. And when we go back and look at the stock market interface, we see... Oh, where is the stock market interface? Didn't provide one? I should have had one here. Well, we can assume, instead of C, that we need to be able to get the price. Looks like it's got some sort of a constructor. It does something with the registry where it rebinds the name of the stock market implementation with the instance that implements it. And then when somebody uses the registry to go and get the stock market implementation, they'll have to cast it to something which is of stock market type, and then invoke things like get price. What's wrong with this get price over here? Can I invoke get price remotely? And the answer is no. And the reason why is because it doesn't throw a remote exception. So if I had it throws a remote exception, then I could invoke it remotely. So get price, yeah, it can be accessed outside of the package, but only locally to the machine upon which it is running. So you can have non-remote methods, non-remotable methods in the same class, but if you want to be able to invoke them remotely, they all have to throw the remote exception. What's up with this security manager here? What's a security manager? We haven't really talked about that before. What's that do, do you think? How does Java get security? Java gets its security through what we call feature limitations. So the security manager defines what those feature limitations will be. So if we run in a secure environment, which has instanced the security manager for us already, then that security manager will already exist, and we'll be able to find its existence, and we'll be able to gain access to it. So when we go to the system get security manager, if we're running in a framework that involves something like an applet in a browser, this may be non-null. It may already be a feature-restricted item. Can you change a security manager once it's been instanced? No. That would be a security hole. You can't just get the instance of the security manager and say, give me access to the file system, because that would be bad. That'd be even worse than flooding the internet with packets, or perhaps just as bad. So here's sort of this the breakdown of the different steps for doing RMI. And remember, we said something about step 1, define an interface for the remote classes, and then compile the interface. And so here's this little interface without an implementation and throws a remote exception. You can always compile interfaces like that separately. You can compose them with Notepad and just call JAVAC on them. Here's an implementation of the remote hello, and what it seems to do is it lets us sort of get a message remotely. Passes, let's see, get message. We don't know what that message will return. I suppose when we get the message, it'll return something. And then here's something that says, aha, the message is hello world. And it looks like that's global to this, so it'll probably return that message. It'll return hello world. Here's a constructor that throws a remote exception. So this doesn't really do much. It just lets us call get message, and then it returns hello world. Separately, on the command line, we have different JDK type commands which we were able to invoke directly. So we could invoke our own RMIC compiler. That's the remote method invocation compiler that generates the stubs and skeletons for inter-machine communication using the marshalling of parameters that we spoke of earlier. So how would I find that RMIC? Where is that at, do you think? Can I just bring up a command prompt and find it? RMIC. Oh, look. It's already in my path. Java minus version. Let's see, does that work? Oh, yeah. So, in theory, I should be able to go to my program files and find JDK 1.7. And in the bin, I can find stuff. And sure enough, the whole RMI package has been broken down for me. I got the RMI compiler, an RMI daemon, an RMI registry. I can invoke this RMI registry right now. I can invoke it right from here. And if I do, it'll use the class path from my present environment. Oh, that's bad. What happened? RMI registry. Type it into more. Oh, he really didn't like it. Is it possible the RMI registry is already bound? Something is running. Is the compute client running? Oh. I think that what I've done is I've resized things so you can't see the... How does one do this? Oh, I see. There's a little thingy here. I'm having trouble resizing things so I can see the console. There we go. Disconnect the server. Now, without the RMI registry being occupied on its common port, it can now run, allow access, and now the RMI registry is running. So what did we find out? That's actually a very good error to see. Very good error to see. You can't have two applications listening to the same port at the same time. Right? Because that is a consumed resource. So if you've got a commonly used registry number like port 1099 and you try and accept connections on port 1099 twice, that's going to throw a socket in use exception, or actually a port in use exception. That's a common beginner's error, and I make it all the time. I forgot to end the registry of the program in the server when I started to invoke the registry. In other words, you can't run the registry twice, but you must run it at least, you must run it once. If the registry is not running, your program had better launch it internally, as my server had done. But then if you try and run it again, you're going to have a port in use exception at runtime. That's kind of interesting, isn't it? So suppose I said start RMI registry. So now the RMI registry is running. What do you suppose would happen if I said start RMI registry again? Well, it probably started and then died. Why don't we just say RMI registry so we can see the error? Yeah, so there it is. You can't have two registries running on the same port at the same time. In fact, you can't listen to the same port at the same time with two different accept methods. So after having killed it, I can now start a new one. So that's key. else is going on here? What's this version 1.2 stuff? What's that about? That means I can generate bytecodes that are compatible with JDK 1.2. It's like from the days of yore. What's the -D for? Any ideas? D stands for directory, yes. D stands for directory. What do you suppose the period is for over here? Everything has meaning in this line. Say it again? No more. No, it means that's the present directory. So it starts from this point in the path. What it does is it's setting up the class path for the RMI registry. So if you go to search for classes, it will actually discover those classes right there. So if you start to register something with the RMI registry, and then you proceed to look for something, it should be in that path. But here RMIC is trying to compile everything in that location and looks for classes there. So here RMIC is compiling the remote hello implementation. The dot, which is down in here, is telling the compiler where to put the generated stubs. That's the path for the output of the stubs.
So you should do that in the console.
Actually, IntelliJ is taking care of that for you. But if you wanted to use some other technology like Eclipse or NetBeans, you may have to actually tell it. So generating RMIC code is something that IntelliJ used to be able to do explicitly in one of its settings. The question of where that is nowadays, I'm not so sure, because things have changed quite a bit. There's usually something in the compiler. There it is, RMI compiler. So I can enable RMI stub generation, and that will do it for me.
So I should check that out.
Yes, you can certainly check it. You can also generate the IAOP stubs. I guess I should ask. Generate the IAOP stubs. Okay, come on. Professor Lyon, what are the IAOP stubs? Really? You guys know what that is? You don't have to ask? Okay, I'll ask you. What are the IAOP stubs?
We don't know.
Ah, boy, I'm so glad you asked. That's the Internet Inter-Orb Protocol, IAOP. You guys didn't know that, right? Just checking. No, what could that possibly be? The IIOP has been established by the OMG. My God. It's the Object Management Group. The Object Management Group has decided that the IIOP would be the Internet Inter-Orb Protocol used by CORBA. More anacronyms. CORBA is the Common Object Resource Broker Administration. I love those acronyms. I love those acronyms. So CORBA objects are used for when you want to do RMI with languages not Java. Like COBOL, a very popular language in Hartford, used by IBM mainframes. In the insurance industry, yes, the Hartford still uses COBOL on IBM mainframes. But new programmers don't know COBOL. So they write it in Java and then use IAOP to invoke the COBOL main subroutines on the mainframes so that they can proceed to use modern programming languages. So IAOP is your connection with old age legacy code. That enables RMI to be used for an application that we haven't discussed before. the use or reuse of legacy code. Legacy code in languages that people just don't even bother with. Right? For example, suppose I wanted to invoke some Fortran at the world's oldest helicopter company. The nice thing about the world's oldest continuously operating helicopter company is you find the world's oldest continuously used helicopter design software. And it's not written in Java. It's written in 4 fantastic flavors of Fortran, culminating in the inscrutable Fuji Fortran 95, which has pointers, but which they still call Fortran. So if you want to invoke those subroutines, you can use Corba. And, of course, the IIOP. But from the point of view of a Java programmer, it's transparent to you. All you have to do is generate the IIOP stubs, and then you can start to use those Fortran subroutines remotely. How exciting! Because what that means to you is you don't have to touch the old style Fortran code, which is really good, because no one can maintain it, because the people who wrote that code are gone. They've gone on to greener pastures. Programmer heaven. So as a result, they left behind this legacy code, which you dare not change because it works. That's the only argument I ever heard about changing that code. You can't change it. Why is that? Because it works. And so, right? I've heard that argument. It's a very compelling argument, actually. People are afraid of changing that code. What else can I do with RMI? Oh, fun things. All kinds of fun things. For example, games. I can play games across a network against other people. So here's the tic-tac-toe game, which allows me to do remote method invocation applications involving a form of communication where we have a client and a server, and maybe the server isn't actually running on the machine where our opponent is running. Maybe the server is the board server, and we both rendezvous with the board server, and the board server maintains the state of our system. So in the case of a massively multiplayer online game, what would be an example of such a game? Wolfenstein or something? Doom? Some massively... No? People don't play these games anymore?
Online.
They're not online? No. What do people play?
World of Warcraft.
What's it called?
World of Warcraft.
World of Warcraft. With World of Warcraft, you will probably have a server that isn't your computer, right? It's operated on World of Warcraft's regional data center, which is probably serving umpteen bazillion screaming lunatics who do nothing but play World of Warcraft all day. And what it does is it maintains the state of each player. It maintains the geometry of your universe, your World of Warcraft world, whatever that world looks like. Probably has some limited rendering on the server, because most of the rendering is done on the client. And so all it has to do, does World of Warcraft have guns?
No. Weapons.
It has weapons, like arrows. So when you fire an arrow into the virtual world, it actually intersects your opponent, and that gets registered at the game server as damage, and presumably causes some bloodiness or something or other, and therefore reduces the, I don't know, I'll call it living points from the opponent until eventually they die or get repaired somehow. So I'm guessing. So maintenance of, I'll call it a consistent state across the network is the responsibility of the server, and inter-client communications all go through the server. So you can use unicast protocol to communicate with the server using RMI, remotely invoke some, I fired the arrow and my opponent is dying kind of thing, and then make sure that the opponent knows that they've been hit. So now RMI, across a network has got this multi-billion-dollar industry which it is capable of supporting. Sony has its own mechanism for doing multiplayer games online. They call it SonyStation.com, and you can use desktop computers in order to be able to interact with other opponents. I used to play this all the time until they started to charge, and that fixed my addiction. It was my sense of thrift that overrode my desire to quash my opponents. So now we have, I think, a very, I'll call it, innocuous board game which we can play over the net. What would be the limits on what it is we can do with our little innocuous RMI board game? Our network-enabled tic-tac-toe board. There's some networking limits. For example, let's say I ran it now. Could you guys play me? Probably not, right? Why? Because you can't even ping my machine, right? I'm on the wrong network. I have to get on the student network so I can play with the students. That's so important. How does one get on the student network anyway? Really? I need a password? I mean, I would like to be able to be on the student network. Connect. Is this going to, like, prompt me for something? No. Am I on the net? Oh, no, I think I'm not connected. Oh, I'm not allowed to connect to this. I can't play a game with my students? It's not fair. I mean, I think it's very educational. The professor should be able to play a game with the students, shouldn't he? Let's see. Oh, I'm on the network. It's good. Can you guys ping me? Can I ping myself? I think we had this discussion already. I've got an IP address, I think, but I don't know what it is anymore because I changed my network. Let me run my compute server here. Okay, so there's my IP address. Can anyone here ping this address? You know what I mean, right? You open up a command prompt, type ping, and then space, and then the address. How you doing there? You can ping it. You can. That's great. Now, why don't you try and run the compute client with this IP address given as an argument? I would like you to run. I'm running a compute server right now on this address, and you confirmed for me that you were able to ping me. So there's this thing here called compute client, you see, and the compute client resides in. Oh, look, it worked. Somebody did it. Somebody ran the compute client. So presumably, if you're in the compute client and you want to run it again, you can type whatever you want to on the screen and it'll come out here. And so what it did was it said, right, this gobbledygook in here, why don't you change it a little bit? Somebody else wrote something. I don't know who's doing it, right? That was you, okay. So why not change the it's 407? Oh, that's good. Yeah, right. So this is what do we call it? RMI communication across the network. This is cool. Yes, it is cool. Yes, very cool. So you could print out your name, or you could print out derogatory remarks about your colleagues. It's now 4:08. Dr. Ryan equals boss. Oh, that's very kind. I better quit while I'm ahead. So there you have it. A real-life application for RMI. Now let me ask you a question. If I wanted to do communication back to your machine, what would you have to do?
Give us a login address.
Well, I mean, I'd need to know your IP address. That's for sure. But also you'd have to run.
Wait, and what?
I suppose I wanted to reciprocate and talk back to
Chat
you.
server.
Well, yeah, like a chat server. You'd have to run the compute server. Right? Right now you're running a client and I'm running the server. But if I want to talk back to you, you'll have to run a server as well. And then we could have peer-to-peer communication. My client would talk to your server and your client would talk to my server. And then we would have a nice chat program talking back and forth. Isn't this fun? Okay, I'm turning this off now. Well, I just thought that was very nice. That's a good demo. It actually worked and everything. So the stubs are being created for us automatically with IntelliJ. We now have a mechanism whereby we can do games, we can do distributed computation, we can do a little bit of program segmentation, but I think what's really interesting now is we're able to do communication with strongly typed data. Right? The strongly typed data is kind of the important part, because before what we were doing is we were just grabbing some strings and passing strings back and forth using sort of a web server, but now we can actually pass instances back and forth, and that's a much more compelling thing. Here's the RMI compiler outputting stubs to a class directory. So that's the destination for the RMI compiler. And you can take a fully qualified class name and output your stubs if you need to. Here's an instance of some remote service, and now I'm going to bind that remote service to my registry, and then it says waiting for calls. So whatever this remote service does, I don't know. But as the RMI registry comes in, it will resolve to the name RMI hello to the instance hello, and then allow people to invoke it. Presumably, people who are looking for an RMI registry with a service called RMI hello know how to use it. If they don't know how to use it, or if they don't have an instance that enables them to invoke it remotely, they're going to have a problem. So at the end of the day, when I'm almost out of time, I just want to say this about name rebinding. I can go into the RMI registry and put in an arbitrary instance into this RMI hello, and if I put in an arbitrary instance and you're not expecting it, you're going to be stuck. Because when you go to the RMI registry and you say, give me the RMI hello instance, and instead of passing back RMI hello, I pass back an instance of payroll, you're going to get a class cast exception at runtime when you try to cast it to something you think you know about and you got back something else. So this RMI registry, this is the tricky bit. I say open a DOS box. What I really mean here is get a command prompt. Go to the start menu, type CMD, or if you're on a Mac, go to your, what do they call this thing? The terminal app in utilities. And then in the terminal app, if your path is set properly, you should be able to call the same exe files in the JDK that I did, including the RMI registry. If I had a Mac here, I would try it. But I don't have one. I do have one at home, but I have one here. In the DOS prompt, if you type start RMI registry, you can just close the window if you want to kill the RMI registry, you can type Control C if you've run it directly from the command prompt. I don't know what they do on a Mac. Is it Control C on the Mac? I think it is. I forget. When you're on a Mac and you type, no, that's Moth C. Moth C looks like a little moth. Have you not seen it? Moth. Have you seen the moth key?
That?
Yeah.
Oh, command.
Moth.
Command.
Oh, command. Yes, right. That's the color. Moth. So if it's Moth C, that's copy. But if it's Control C, that should kill the RMI registry after you invoke it. You don't call it the Moth C? No.
Or command.
Oh, it says command on it. Yes, I don't. Mine doesn't say that. I don't remember when I started calling it Moth. But my first Mac was a Mac Plus. Or Mac, no, my first Mac was a Mac 512. A thick Mac, which was the one right before Mac Plus.
It is Control C.
Control C, yeah, I thought it might be. So this is what I would do from the command line. I would type start in DOS, Java, which would run the Java virtual machine, and then RMI hello server, and then that would invoke the RMI hello server in its own task inside of a window in DOS. For the Mac, which is really Unix, I would type Java space RMI hello server, and if I wanted it to run as a background process, I would say space ampersand, and then that would launch it in the background and give it the status of a job, which I would then have to kill later. Am I doing on time? Almost done. So what I've done here is I've created an instance of the RMI security manager, but I commented it out because I didn't need it to run. Here's the protocol for going to RMI localhost. Here I did the lookup for RMI hello, and then I cast it to RMI hello, so it's clear. If you look up something like RMI hello and it doesn't return an instance of the RMI hello interface implementation, you're sunk. So RMI hello is an interface. The RMI hello implementation implements the RMI hello interface. I think I said that right. Then if I say hello.getMessage, it goes out to the remote method, grabs hello world, and then prints it out. And then comes the interesting thing about bytecodes and how to build a bytecode server so that you can find classes dynamically at runtime without having to get them off of your file system. And for that, you need to have an interesting class loader. Interesting because it's not the kind of class loader you're used to. This is not the Java virtual machine class loader that looks for the class path and then proceeds to load classes based on that. Normally, when you run the Java compiler, you output classes whose unfortunate suffix is .class. I don't know if you've noticed that. You guys noticed that, right? Javac outputs class files. The class files are really nothing more than repositories of bytecodes. And the bytecodes have to be loaded dynamically at runtime by the virtual machine in order for you to do a successful invocation. So when these bytecodes are loaded and they're not on your file system, it's possible for you to get them from the web. So you can create a bytecode web server which allows you to load those bytecodes from a class path that isn't local to your machine. Class path that goes in across the net. And you can use arbitrary protocols in order to be able to load your bytecodes. In fact, you can create, and I have created, my own class loader so that you can do interesting, wonderful, and exotic things with bytecodes, which is beyond the scope of today's lecture. So that's what I have for you today. I would wholeheartedly encourage you to read chapter 43. I think there's something coming up called spring break. Heard of this thing? So have a nice spring break. Is anybody going anywhere for spring break? Oh, yes, where are you going?
Boston.
Oh, that's nice.
Baltimore.
Baltimore, that's good. Boston's nice too.
I like Boston.
Do you live in Boston?
I've been there.
Okay. Any other good places people going? I'm tell you, I have a plan. I'm doing paperwork. That's what I do. I'm grading your midterms. So have a nice break. If you have midterms after the break, they won't be in this class.
Can you help me?
Sure.
I don't know what to do with this.
Let me turn the recording off.
Yeah.
Oops. I'm falling over myself here.